What's going on with this identity? This identity is not new. It's not different. It's not based on the new stuff. It might be a little bit trickier than some of the ones that you've done, but for the most part, you're capable of doing this. What would be, let me get this started. What would be your gut? Sine theta minus cos theta, and the right side is secant theta. What do you think? Very good. Somebody had an interesting idea this morning. Change this one to 1 over cos. And the only reason why you might do that is because we're going to change everything else to sine and cos. I know I'm done on the right side after that. Maybe I do that first. You don't have to. But I think it's an interesting thought. I see a lot of people doing that. It's a good idea. And then change the tan to sine theta over cos theta. So that's minus 1 over sine theta minus cos theta. Okay. Hopefully that start is obvious. Now what might you do?
At the top, you're going to add the sine theta over cos theta minus 1.
How would I do that?
So you'd have a common denominator of cos theta, so it'd be sine theta minus cos theta all over.
Very nice. And interesting how just like when we were reducing those tan ones yesterday and we did root 3 over root 3, like this is the same, right? And it's funny how all of a sudden that starts becoming clearer for people. And we see some of the parallels between what we've been doing, even though it wasn't identities and identities, there are some parallels. Some people might think you multiply by a conjugate on the bottom. That's a little bit tricky. There's reasons why we probably don't want to do that, but people see sine minus cos and they automatically start thinking Pythagorean identities or that kind of thing. But it's unlikely that that's what we would want to do. Part of the reason is because it's going to add squares. We don't have any squares over here, so we don't probably want that. Max, what are you thinking? Oh, that's what they just set up here. Very good. Yes, you got it. Cos theta over cos theta. My thetas look weird for some reason. Theta equals. Oh, whoops, not yet. This one is a little bit strange because I think for some people they don't quite see. So I'm gonna complete this step, but they don't quite see what's gonna happen. And the next one that we're going to do is very similar, although quite a bit more complicated. It's not as obvious what will happen in the next step. Some of you it is because you're good with fractions, but for some of us it's not. And there's a lot of hands up. Did I make a mistake or? Okay, sometimes I worry I made a mistake because there's like a whole bunch of people trying to tell me something, but it's just, okay, you know what to do next. That's good. And so what do you do when you're like, I'm not sure what to do next. So some of you know what to do. That's good. Before you tell me what to do, what observation would you make? What would you notice in this that might give you a hint or like might give you some indication of what to do? Tyler, what do you think?
Well, there's a sine minus cos in the top half of the equation, and there's a sine minus cos in the bottom half.
Very nice. And in some cases, it's really obvious what's going to happen with that. But in this case, maybe it's not so much until I do the next step. And so you might be like, okay, I see the same thing there. I'm not sure if they cancel out. I'm going to try and find out. Like I'm going to do the next step and find out and see if they cancel, because if they do, that's good. If they do cancel, what else do you notice? Yeah, like I got a something over cosine here. And that's 1 over cosine. So that's kind of a good, like I'm on the right track here. So there's a lot of things that you could observe, that you could notice that might lead you in the right direction. Again, if we think of this as sine minus cos over 1, I'm going to go sine theta minus cos theta over cos theta times flip and multiply. So 1 over sine theta minus cos theta. And sure enough, even though those are adding, and usually we can't cancel when we're adding, in this case you can, because it's a whole term. And so that does divide to 1 with that. Okay, and then we're done. Adam.
Can you just like, when it's that like 3-layered fraction?
I would write over 1 and then cancel, and then write your answer. Then it looks a little bit more clear. Then I know you know what you did, and I know what you did, and we're both on the same page. Kind of like yesterday when I said, if you have something over root 3 over something over root 3, those 3's are going to cancel. Like I said that yesterday, so, but I would show both as a fraction. Any questions? Any questions? Okay, here's another one. Keep these ones nice and spread out. You're going to need a little bit of room on your page for this one. I will zoom back in once I get this done, yeah. So what jumps off the page that's different about this one? Adam?
Well, like in your final answer, you are going to have x's and y.
Oh.
Well, like on each side.
Yes. Yeah. I didn't even think about that, but we haven't really done identities that have like two different variables in them. Yeah, very good. What else? Brad, you hand
I was going to say that there's more than one variable.
Yeah. Good. Isaac?
You can combine those in the equation.
Okay, that's what we're going to do. Yeah. And also, so there's more than one variable, but also there's like an x plus y in the angle, right? And so this is clearly a compound angle identity. That's what makes these easy. And I think I said this earlier in the unit that like, okay, we're going to add in some grade 12 identities, but it doesn't actually make it that much harder. Now there are some sort of new tricks to this, and there are some new characteristics. But it's obvious when you're looking at a compound angle identity, because I've got x plus y on this side and I don't have x plus y on the other side. If I had x plus y on the other side, then it's just like I could just replace that with an a and move on with my life, right? Like then it's just the same thing. But it's the fact that I have x plus y on this side and the x's and y separated on the other side. And the only way we know how to separate those angles that are added together is with our formula. So our first step is obviously going to be the formula. And for the most part, the next thing that we're doing, which is double angles. So we start that tomorrow. Then we're going to do identities with them on Friday. For the most part, they're pretty obvious as well. When you're dealing with a double angle identity, there's pretty strong indication that that's what you're doing. It might not be quite as obvious, and there's some things about it that's harder, but for the most part, you know that first step. So our first step here is use the formulas. You can go ahead and do that and expand. We're adding and subtracting, so you need big brackets around the outside of both of those, right? Make sure, because we're still multiplying one by the other. Sometimes I use square brackets because a C, if it's not drawn properly, looks like a bracket. Now what do we do? So sometimes these ones, I think, again, it's not as obvious what the next steps are going to be. Like you've never done one quite like this. And so those of you that are confident, who have your hands up right now, maybe you have a good idea of what to do. But other people are going to sit there and be like, well, maybe you could do this, but I don't know if that's what you're supposed to do, like, because it can't look a few moves ahead. So, like, my question to you would be, what even can you do here? Like what's even possible to do? Some people think I could go and change the 1 to something, and that might work, but usually that's a terrible idea, because usually, like, do I change that to a sine x and sine squared x and cos squared x, or sine squared y and cos squared y? Like, what do I change that to? So that's not usually a great idea. What's even possible to do?
It's a difference of squares, so it's getting it out.
Okay, so even if it wasn't going to turn into a difference of squares, I could expand this. It's a disaster. It's going to be huge. But what else could you do? And sometimes that's what identities are all about. Is I think some people hesitate. They're like, nah, that can't be right. That's way too big. It's going to be like 4 pages long. That can't possibly be right. Well, it turns out that's actually what you're supposed to do. So sometimes you have to ask yourself, what else could I do? Okay, and if you notice that it's something minus something and the same something plus the same something, those middle terms are going to cancel out like a difference of squares. And so you can cut out the middle step, and we can go straight to, it looks like this: cos squared x, cos squared y, minus sine squared x, sine squared y. The middle step would have had this disaster: cos x, cos y, sine x, sine. Like it, but this is something that might happen to you. You might get a big muddled mess that has to be expanded, and there's disastrous stuff in it. That does happen. Okay, and then minus sine x, sine y, cos x, cos y, with these two bottom terms out on the outsides of that, right? If you actually did the full binomial expansion, you'd have these two terms, but they're the same, even though I wrote them in a different order, and they would add to 0. Isaac?
So what side is the 1 mark?
Say it again?
Because you turn 2 middle terms into 1, right?
No, there's 0.
There's 0?
Yeah. Look, it's the same thing minus itself. Right? Just like when you have...
No, sorry, I'm talking about the next step. Like cos squared y.
Good point. That's not true, though. And some people try to do that. When you have a cos squared x and a sine squared x, but any other junk, that's not the same identity.
Sure.
Okay? So that's not going to work. So now what do we do? If you're ever stuck, remember, one of the big strategies is look at the other side. What do you think?
Wait, are we allowed to use like the other identities?
You can use any identities you want at any point in time as long as you use it correctly. Whether it's going to help or not, I don't know.
So I was wondering if we would turn the sine squared x into 1 minus cos squared.
Why in the world would we do that?
Because on the other side we only have cos squared.
Anybody else notice that? On the other side, I only have cos x's. On this side, I still have sine x's. That's an indication that that's something you could try if you're stuck. Absolutely 100% great idea. I've got cos squareds and sine squareds, and because they're squares, I can use the Pythagorean identities. Okay? So let's try that. What does that look like? Cos squared x, cos squared y minus... So sine squared x turns into 1 minus cos squared x. And sine squared y turns into 1 minus cos squared y. And some people go, that didn't help. This is even more complicated. Well, sometimes that's what happens, and you just got to keep going. So I would ask the same question we asked before. I'm not really sure what to do. What could we possibly even do? Adam?
You can expand it again.
Expand it again is going to be another big disaster. This one doesn't have that middle term disappearing. Let's do it and see what happens. And if you try to do a little bit of it in your head, you see some good things coming out of it. Okay? So cos squared x, cos squared y minus 1 times 1 is 1. Oh, I got minus 1. I got a minus 1. That's good. 1 times negative cos, so this is negative cos squared y minus cos squared x. And then negative cos squared x times negative cos squared y is positive cos squared x cos squared y. And what just happened there? I've got cos squared x cos squared y here minus, same thing. So that's going to go away, and I'm going to be left with what I need. So I'm just going to show that one last step. Cos squared x cos squared y minus 1 plus cos squared y plus cos squared x minus cos squared x cos squared y. Gone, gone, and we're done. Any questions?